I'm Daniel Frisch and I'm presenting my paper Association-Free Multilateration based on times of arrival. Before we begin, I want to say thanks to our cooperation partner Frequentis Comsoft in Durlach. They funded this research and also provided us with real datasets that we will see in the end also. We'll work with times of arrival measurements that are transmitted by multiple targets where the messages are indistinguishable from each other. The messages are captured by a network of passive receivers at known locations, and the receivers are time synchronized with each other. And based on these times of arrival, with our novel multi-target multilateration algorithm, we calculate the positions of all targets. These point estimates are independent from prior time steps. No tracking is involved here. And the methods we use to achieve this involve maximum likelihood, Wasserstein distance, the Hungarian algorithm, and nonlinear optimization. In basic multilateration, we have one target that transmits a radio message, which then propagates with the speed of light. And on the time axis, we have the target transmission time in the beginning. And in this example, sensor 1 is closest to the target. Therefore, it will receive the message first. Shortly after, also sensor 2 and 3 receive the message and will record the respective time of arrival. And the accurate mathematical formula goes like this. The time of arrival at the sensor equals to the target transmission time plus the Euclidean distance between target and sensor divided by the speed of light. Very simple and easy. We have a system of nonlinear equations that we can iteratively solve for the unknowns. The unknowns are target position and target transmission time. This can be done starting from some initial guess of the target transmission time and target position that is temporarily hypothesized here and plugged into the formula. And based on this, we calculate the hypothesized time of arrival, subtract it from the actually measured time of arrival, and from this difference we take the sum of squares, use this as a distance measure, and define it as objective function for any off-the-shelf continuous optimization solver, which calculates the optimal least squares solution of this problem. Now in the multi-target case, we have more than one target. And if these targets transmit shortly after each other, then also the times of arrival will be shortly after each other. And here we can see, for example, on receiver 1, the first time of arrival comes from the red target, but on receiver 2, the first time of arrival comes from the blue target. So it's all mixed up and we cannot tell which time of arrival comes from which target. We call such a situation a dense transmission event, and it transforms the problem into a mixed, continuous and combinatorial problem due to the unknown permutation parameter that comes from the association. In our objective function, we then have to sum not only over the sensors I, but also over the targets j. And we have one target transmission time and one target position for each target, and one time of arrival at each sensor from each target. However, we don't know the association between this target index and this target index over here. Therefore, we have to add another variable, a permutation parameter that addresses for this variability in the association. Then we use the Wasserstein distance, and the Wasserstein distance is defined in such a way that we select that one permutation such that the overall distance here is minimized. So when we have a set of hypothesized times of arrival and actual times of arrival, how can we find this permutation in such a way that the overall distance is minimized as much as possible and find that efficiently? In a very simple setup on the time axis, suppose we have 3 hypothesized times of arrival and just one actual time of arrival because the messages from the other 2 targets were not received at this receiver. Then it's obvious to see that we just have to associate the nearest neighbor, which is computationally simply finding the minimum of a vector, so very easy to do. The next case is when we have again 3 hypothesized times of arrival, but this time all messages were received, so we have also 3 actually measured times of arrival. Then this one would be one possible association, but certainly not the one with the smallest overall distance. This one yields the smallest overall distance. And we can see that we just have to associate the earliest one here with the earliest one here, and the second ones and the last ones. Okay, so it's computationally just about sorting the vectors of times of arrival, because we have a one-dimensional problem here. So that's also easy to do. The only case where it's getting more elaborate is when we have different numbers of times of arrival, and they are not like one, but more than one and different. Then we have to solve the linear assignment problem, for example with the Hungarian algorithm, to come up with the Wasserstein distance. Finding the Wasserstein distance can be seen as a second minimization problem inside the objective function. And once we have the Wasserstein distance here, as discussed on the previous slides, we give it back to the outer nonlinear optimization algorithm, which then proceeds to find better hypotheses of the target position and target transmission times, until in the end we get the optimal least squares result for all the targets. Now we will have a small simulated evaluation. We define this arrangement of sensors, and we define the true target position here with 2 targets, and these are the true target transmission times, 0 and 0.5. Then we use some initial guess, just randomly selected here 2 target positions and the corresponding target transmission times. Same here, another choice of random guess for the initial parameters. Then we do the first iteration, the second iteration, third iteration, and so on, until we find the true target positions and also the true target transmission times for both targets. Here is a simulated example with 3 targets. 100 random initial guesses were used each, and the resulting point estimates are colored by the final Wasserstein distance. And as we can see, the true solution usually corresponds to the point estimate with the smallest Wasserstein distance. Therefore, we can recognize the global optimum. But also we have numerous local minima here that we can recognize by having a higher residual norm, and we really should use more than one initial guess to make sure that we find the global optimum. Now this is a real data example with data that was recorded by Frequentis Comsoft in one of their nationwide wide area multilateration systems, quadrant sensors. And this one covers the area of one airport. Here are 4 targets present that are assumed to have the same mode A codes and therefore have indistinguishable messages. 2 of the targets are flying in close formation, which is considered rather difficult for multilateration, and even in this case our method was able to get the correct point estimates. Again, all the point estimates are independent, there is no tracking involved here. Here is one more real data example with our method and without our method. And as you can see, we were able, for example, to rule out all these fake measurements here that can be very annoying in air traffic surveillance. Summarizing, we propose a method for multi-target multilateration that can be used if the associations between times of arrival and transmitting targets are unknown. We only require a network of passive synchronized sensors. Our method is very reliable and we provide independent point estimates. This method is also patented by KIT and Frequentis Comsoft. Thanks for watching.